Okay. So.
Yeah, please go ahead.
So thank you. So thanks everybody. It's great pleasure to have this opportunity to discuss with you our recent results. And I will be talking about something that we call phenomenology of spectral functions in finite disorder spin systems. These two words which I underlined, like phenomenology and finite systems, are important. Yeah, you will see soon why. And this work which I will be discussing today, it was put on archive last Friday, and it was done together with Lev Widmar, Janez Bącza, and also with my student from Wrocław, with Bartosz Krajewski. Okay, so let me, oops, okay. Let me start with the motivation. So the motivation for our work is the slow dynamics in disordered chains, which is observed by many people in many experiments. And yeah, what we study standard model, which people mostly are interested in this for this disordered chain. So we have Heisenberg model with disorder, and these random potentials, they change from -W to W. And of course, the most important problem for this model, which people have been interested for some time now, is the ergodicity breaking. It means that if one starts from some particular quantum state that up to arbitrarily long dynamics, we still see that the properties of these initial states are reflected in the final state. It's also the case for this famous experiment which measures imbalance, that one has disordered lattice, one puts, this is called atom experiment. So atoms are put in this, let's say, every second site, and then the system is evolved in time, and one checks whether after a long time, this pattern which one observes is correlated with the initial pattern. So of course, the main question is what happens if we calculate, what happens, yeah, if we could calculate this autocorrelation function, so the relation between the initial and the long time state. And this we will study using this autocorrelation function. Of course, the challenge is to have first infinite system and then to go with time to infinity. These limits do not commute, so one should be a little bit careful. Anyway, this is big challenge, and mostly this challenge cannot be achieved This challenge cannot be achieved in numerical calculations. And why? The problem is that whatever we do into numerics, we have only small systems. So, and of course, in order to answer this question, we tried with the small systems, we try to go to long times, and this is a big problem. Here, this question of ergodicity would be somewhere here at long times. But one can also always criticize that such dynamics for small systems and large times, it is very opposite what we see in this limit. So we tried something different. So we tried, of course, small systems, but we tried to see what happens at short time scales. And our aim was to find something useful from this slow dynamics, which is, it's observed, as I said, by many people, and what we can learn from it. So this is quite long talk, so maybe quite short talk. So I maybe could start with announcing the main message, and then during the rest of the talk, I will try to convince you that maybe we are correct, or maybe we are, you will find we are not. Anyway, so our initial or starting point is also disordered system, but without many body interaction, like this XX model plus the disorder. And this is, I think, without any doubt that this is a system which is localized. It has a lot of local integrals of motion. So this sounds strange, but these local integrals of motion, one can think that they are just occupations of Anderson states, and also products of such occupations of Anderson states, which commute with Hamiltonian, and then they don't decay in time. And our main message or main conjecture in this phenomenological treatment is what we try to do. We tried to think that at least for certain parameters, for which parameters you will see soon, that if we add interaction to this model, so we go from XX model to the Heisenberg model, then maybe this interaction can be treated as a perturbation, which breaks integrability. And maybe certain Lyons with these local integrals of motion, we will call that they will become delocalized. It means that they will not be strictly conserved. It means that they will have some relaxation time, or decay time. And maybe these decay times are reflected in the slow dynamics in this regime of frequency for which we can get, I think, reliable numerics. Okay, so what we study and exactly, so we study imbalance. So the same imbalance which was studied in this famous experiment, the same imbalance which was studied by many people. Why we do it? First, because it was measured. The second reason why we study this quantity is because this is self-averaging quantity. So once one could reach infinite system, there will be the same result for every realization of this order. But for us, other thing is the crucial point, that this quantity has projection on many Lyons. So it is like these occupations of localized understone states, which are in many places of the lattice. And this quantity has projections on many of them. So what we do for this operator, we calculate this autocorrelation.
Marcin, question.
Yes?
Why the square root of L of system size instead of a system size in definition of A?
Okay, this is for convenience, because we would like to, this average here, this average is average over infinite, over infinite, this is infinite temperature ensemble. We would like to have this average at time 0, 1. So that we do normalization to have it 1, okay, to simplify the, let's say, discussion of finite size effects. But this is not essential, okay? This is just this normalization to have this A at time 0, that it should be 1. That's it. Okay, so we do Fourier transform. This is nothing strange, but we do one more thing. We integrate this Fourier transform from minus omega to omega. And this might look strange, but this is extremely useful for the numerics. Let me explain you why. After one integrates this Fourier transform, what we get for this integrated part are just all matrix elements of this operator, such that the eigenstates which come here, m and n, the difference of energies is smaller than this omega. So this is easy to calculate. And this plot, this plot illustrates how it works. For instance, you what happens. So this continuous lines, this oscillating continuous line is really real-time dependence, but this dashed smooth lines, they show this integrated quantity, this integrated Fourier transform as a function of 1 over omega. So one can see that it reflects very nicely this long time dynamics, which we want to study, but it filters out these oscillations. And this is very nice, because in the numerics, we really extract this physics, which we would like to discuss. Okay, so now...
sorry?
Yes?
Can you go back to the previous slide? I mean, this behavior that you see by filtering out the frequencies will be the same if you do some time average over a small time window, or is different?
No.
I mean, if you take...
yeah, it would be, yeah, it must be this. I don't know if you can do small time window, because you see, for instance, to filter out these oscillations, this window would be need to be need to be big. So it is not so efficient in filtering. Yes, this is really, really efficient in filtering these oscillations.
Okay.
Of course, it works for the correlation functions which decay as power laws in time. Then it's really a nice trick.
Marcin, do you? Sorry, Kuba, but I woke up. So do you really think that the oscillations up to time equal 10 have any relevance for what is happening, let's say, a long time?
No. We don't think that these oscillations have relevance. So
Thank
this
you.
data, no. This is something that for us it's problematic to get like fitting or something like this. So this data which you see here, they are averaged over, I don't know, like 10 to power 3 realizations of disorder. But so our aim is, you see that after this filtering, we really can follow each realization of disorder. So one of this is one of the main ideas here, is that we don't need to do averaging over disorder, because you will see it can produce the averaging, it can produce some artifacts. I will discuss it later. Mm-hmm. Okay, so now what you see here? This is this integrated frequency, this integrated Fourier transform as a function of frequency, and you see two types of lines, and these two types of lines. So continuous lines are for the Anderson insulator without interaction, and the points are for interacting systems, so for Heisenberg. And this is really, you see, nice single realization of disorder. Okay, this is single realization of disorder. So we really have nice lines. Okay, so what is the basic assumption for our phenomenology? So the basic assumption for our phenomenology is that for the Anderson insulator, we essentially at quite broad range of frequencies, we see very weak dynamics. I would say the dynamics is not completely eliminated, but it is strongly suppressed. So this is like, we don't go to zero. Please see, we go to the frequency where we cut our data. As I announced at the beginning, we don't want to go to infinite time. We want to stay in the frequencies which are above the Heisenberg time. So yeah, for the Anderson, it's flat. So we can say that this integrated spectral function is a constant. It means that before integration, it must be some delta function. It's not so surprising that this is some prefactor here, and then there is delta function. But once we turn on interaction, you see that it changes very much, so that we always see some dynamics, and this is the slow dynamics. So this points, they slowly go down. Okay, so of course, then you can say, okay, this is one realization of disorder. Maybe I have chosen something, some particular realization. No, this is, you can see some 6 other examples, randomly chosen realizations of disorder. The physical or the dynamics is always the same. No dynamics or almost no dynamics in Anderson insulator, and non-trivial dynamics, which we would like to explain for interacting system. Okay, and there's one more point. Here, if of course we can produce infinite number of such plots for different disorder strength. So this is one realization of disorder, but there are different disorder strengths. It means that these potentials Hi divided by W are the same for all curves in single panel. Okay, and then we could try to find what is the correlation. Yeah, because between this endpoint at the Heisenberg frequency for the interacting system and non-interacting system, and this non-interacting is here. I not interacting is here. You see always that these points for non-interacting are bigger. They're always bigger. So I think now I can come to the conjecture, which we then test, and so okay. So let's start from non-interacting system. So the spectral function, this is some quantity, we call it stiffness. This is simply the average of the diagonal matrix elements of the operator. And then there is a delta function. There is this stiffness. Okay, and then if one recalls some important information from the studies of other integrable systems like XXZ model and so on, we know that these stiffnesses of local operator, there is one-to-one connection between the stiffnesses and the local integrals of motion. One can go, the most famous one is that one can go from local integrals of motions, or if you prefer local charges, to stiffnesses using Mazur bound, but one can do also the opposite. One can use this stiffnesses of local operator to construct Lyons. This is, here we need this standard way. So yeah, this is called the Mazur bound, and this Mazur bound says that this parameter here, which comes with the delta function, it seems like it comes from the projections. Projections are again here nothing else but the infinite temperature averages of this operator and the Lyons. So yeah, so then for non-interacting system, the spectral function, it is given here by these projections, and then it should be multiplied by these delta functions. Yeah, and this is the stage, this Mazur bound. This is the stage at which we can switch on our assumption that certain Lyons, certain integrals of motion, when we add interaction, that then they will acquire some finite relaxation times, and that these delta functions will be broadened. That these delta functions will be broadened, and that will give us this dynamics which we observe. So the part of the spectral weight from the delta function goes to finite frequency due to the broadening of these delta functions. Okay, that is fine, but can we support such claim from other studies? And yes, indeed we can. So some in completely different context, in the context of the translationally invariant XXZ model with some perturbation H prime, which breaks integrability. We have essentially some time ago, it was already 6 years ago, we studied these spectral functions, how the spectral functions look like. And again, these plots, they show this integrated spectral functions for different parameter alpha, which breaks integrability. And okay, there are two messages which from that study which we will need again. That first, you see that all these points here is omega divided by alpha squared. Alpha is this integrability breaking strength. That all these curves, they can be nicely fitted by arctangent. And where it comes from, it simply comes, arctangent comes from integrating the Lorentzian. So this is good. So this broadening most probably we can do introducing Lorentzians. And then, but please also remember that there are different prefactors here. So even for the simple model, I mean simpler for analytics and numerics, we see different relaxation times for different integrals of motion. Okay. So now I can fully explain our phenomenological approach. So we have this non-interacting system. We work with this window of frequencies, so we think we work only with the spectral weight, which is here in this finite window of frequencies between Heisenberg frequency and, let's say here, like, I don't know, something like of the order of 1. And then that was our phenomenology, which we tested, that for non-interacting system, we have only Lyons, only this delta function, these local integrals of motion, which produce this delta function, but then interaction broadens at least certain. We don't need that all are broadened. We essentially cannot test what happens at smaller frequencies. So it's enough to assume that certain part is broadened and it becomes Lorentzian. And this part, which is broadened, so this changing part of the spectral function of this plot, we will study further on, and this is the regular part. Okay. And now at this point, so instead of this delta, we have Lorentzians where this tau are finite. And at this moment, what comes into play is why we needed imbalance, not some other operators, because for imbalance, we can expect that here we have summation over many Lyons. It means that instead of, if we don't know these projections, if we assume that they are roughly equal or they are of the same order of magnitude, then from this summation we can go to integrating to the integration over some distribution of these relaxation times. We know that they can be different. Okay. So now the last thing which we need is what could be some reasonable ansatz for this distribution function. And okay, so as far as we know, it has not been. What would be this? What again? Let me stress. What would be this tau? So this tau, so it will be some relaxation time for Anderson lyons. So for occupations of Anderson states. And yeah, up to our best knowledge, it has not been studied before, but some time ago we studied it for much simpler system for Anderson insulator, which is coupled to very different bosons. We really tested different types of bosons, like hardcore bosons, where the energy spectrum is bounded from above, are normal bosons. And for strong disorder, we found that this is the distribution of the relaxation times of the Anderson states. And you see, this is log-log scale, and this is cumulative distribution function. We see that in quite broad. First, we see that they are really broad, that they go over a few orders of magnitude, and they are power law. Not everywhere, but they are power law. Okay. I think I should speed up. So I skipped one presentation. Okay, so what comes out when we combine these two features? That we have a power law relaxation of relaxation times, and we have Lorentzians. What would be the spectral function? And this is, one should just need to do this integration. It's quite simple. One observed this kind of spectral functions depending on this exponent mu, and of course we assume that these relaxation times they are in a certain range from tau min to tau max, and you see that we observe relaxation functions which, as I will show on the next slide, they are very nice. I mean, there is some part like would come from below for frequencies below the inverse tau max, it's flat. Then there is power law, and this power law really covers, it can cover really very broad range of frequencies. Here we put on this, for this plot, tau max 10 to power 5, for tau min just 1. So you see everywhere between tau min and tau max, it looks like a power law with the exponent, and finally it goes to Lorentzian between tau min. What I want to stress now is that we really don't need to insist on the Lorentzian, because you can think, okay, we introduce something really strange like Lorentzian. Why Lorentzian? One can test it for any other delta-like sequence, and the simplest choice is this box function. And even for the box function, one immediately gets that the spectral function in this intermediate range, it goes with 1 over omega to power 2 minus mu, where mu is this parameter of the distribution function. Okay.
Sorry, I didn't get this mu, where it comes from. I mean,
where it comes from. So look, this is okay. So these are the, we don't know it for the Heisenberg model really. We know it for the simplified models, that we have this broad power law distributions. This mu, I mean, this mu.
is a fitting parameter.
Yes, it is a fitting parameter. Okay.
I see.
And okay, and here maybe there is one important thing. Once mu becomes larger than 2, this is funny, but once mu becomes larger than 2, then this log-log plot of the spectral function, it looks pretty much like a single Lorentzian. So you don't need this, you don't see this broad distribution if this mu is larger than 2, because it looks really like Lorentzian, flat up to certain value and then going down as 1 over omega squared. So we would need the broad distribution of relaxation times. So this mu will be fitting parameter. Okay. So now I would like to stress that this type of we don't want to say that we have found any new frequency dependence. This frequency dependence, which is close to 1 over omega. So mu close to 1. It was found in many papers. We found it a long time ago with Peter and Jacek Herbrich. And these are exactly the same. These are exactly the same average spectral functions, regular part. These are numerical data. You see 1 over omega, but it was also found in this, not exactly the same quantity. So I don't want to mix too much, but this is really related in this paper, and also recently, I think by Dres Sels and Anatoly Polkovnikov, they also see this omega dependence. So you see this feature, which comes in numerics, I think out of question, it can be simply modeled by this set of Lorentzians, which we add with us.
Marcin, I'm very, very sorry for disturbing. One question: these plots which you're presenting right now, it seems like some of them are experimental one. Can you make some very short remark of what sort of experiment it was given in these articles?
This is numerics. This is numerics. This is pure numerics. Okay, so this is full diagonalization of the same model. Yes, and this is the disorder strength. We also have this wiggle line where we could reach huge systems with approximate method. This is like Lanczos time propagation, but there is no big finite size effects. The differences here are like this, that in these two papers, one does not study imbalance. So as far as I remember, one studies SIZ, where I is local. So we pick up one site and we calculate, or they study. This is also numerics. Similar correlation functions. Then they do Fourier transform. This is spectral weight. There are some more details, but let me maybe, because I don't have, do I have still some, can I go 5 minutes?
Yes, it's okay.
Yeah. Okay, so okay, maybe I can skip it, but let me show how it works. So how it really works for stronger disorder. So you see that these are again single realizations of disorder. These are points which are fitted by this spectral function. We have these fitting parameters tau min, tau max, and mu. And essentially, for different disorder strength, we can fit very nicely up to disorder 5 or 6. We can nicely fit every single line. And okay, and of course the same is even better if we first average the spectral function of the disorder and then we do fitting. Then it is even nicer. I think this one cannot complain that we do something wrong. But please note that please note the values of this disorder strength for which the same approach works. So we can start from W1, very weak disorder. This anomaly is very small, but we can go from W1 with the same phenomenology up to W6, and these fits are very, very nice. Okay, so what we can learn, and this will be probably the main message. So the main message concerns, of course, what happens with this tau max. So again, we have some distribution of relaxation times of this. We assume certain Lyons are not really conserved. We have distribution of this tau of this relaxation times up to tau max. How tau max behaves. So left panel shows how it changes with the disorder. From average correlation function, this is linear scale. Here is the log scale. You see it goes approximately it goes exponentially with disorder. The distributions are broad, but you see
Marcin,
they are
sorry, I got confused.
Yes.
Can I interrupt? I mean, anyway, we have discussions, so
yes.
Don't be stressed with time. I left with.
Oh, I think I am already behind the schedule. So go ahead.
Okay, I don't understand because you fitted 3 parameters, right? Tau min, tau max, and mu.
Yeah.
Okay.
Okay.
So, wait,
this which they are here marked in blue. Okay. This
so
mu.
there are 4 parameters which are fitted.
Yes.
So you can fit the elephant, but okay.
Okay. Yeah.
So on this plot which you have shown, there
Yes.
is fitted tau, right?
Yes.
There is fitted tau for different disorder values, right?
Yes.
Okay. Thanks. So this is what I wanted to
Yes. So here we fit every sample, but you see, coming back to the elephant, I mean, if you look at this what comes out, what is tau max is really, this is very simple, because it means it is really the time where it stops to follow this this power law dependence. Tau means is essentially not important for these fittings. It is just the beginning where we see here, we start here. We don't want to go to this high frequency range where we see dynamics in the, and then this mu fits the slope, tells you what is the slope. Yes, so it's not so let's say involved combination of relaxation or fitting parameters from which you can really fit elephant. Okay, yeah, this elephant must have some range and must be curved. Yeah, okay. And so we have distributions which are broad. It means that we always see large sample to sample fluctuations, but you see that when we increase disorder, this disorder strengths are equally spaced. This is log scale. This curves more or less shift parallelly and quite quickly for disorder of the order of 2, 3, 5. This tau max goes beyond the Heisenberg time. Okay, so I think I should briefly come to some. I should skip many parts, but I should come to some picture. Okay, so this is what we do. So we have some accessible window of times which we think they are reliable between this low for this quite high energy, and then we go to this should be inverse. Sorry, it's wrong. It should be 10 over J to Heisenberg time, and then we have these relaxation times which are in this window. This is for weak disorder. We see tau max below the Heisenberg time, but for strong disorder or not even so strong, we see that this tau max very quickly crosses this Heisenberg times. And what is going on here, we see essentially we cannot discuss in details what is the dynamics, because we are already with frequencies which are below the level spacing. So this in finite systems, we see this as simply as Lyons, because the relaxation times are below the inverse level spacing. We really see this as Lyons, and here we see this as the localized Lyons. Okay, I think maybe one possible scenario, what we want to say with this. Okay, so what could be the possible scenarios? Of course, this is the main challenge. What would be in the infinite, could be in the infinite system. So of course the question is here. Of course the question is here. What happens with these relaxation times which are above the Heisenberg time? It's possible that they become really infinite and we really have localization, and we don't claim anything that there is no localization at this moment. Okay, it's also possible that this upper limit of this tau max will become larger and larger, will approach the Heisenberg time, but will not go above. So we don't have really local integrals of motion. And in this case, we would see asymptotic subdiffusive dynamics, because this intermediate power law dependence, this corresponds to subdiffusive dynamics. But it's also possible that this times tau max, they will always stay when we increase the system size, because then this tau max will always stay below the Heisenberg time and our dynamics will be diffusive. And then we would see just transient subdiffusion. What we see the subdiffusion in many results. And these are my conclusions. So let me briefly just say so. Our main assumption for our phenomenology is that certain integrals of motion, we don't need to say that they are this all, they acquire some finite relaxation times, That fits numerical data for various disorder strengths. We don't need to do any averaging, and this I think is nice, because otherwise, this can go to we can go to problems. We are consistent with previous numerical data. And of course, we want to say we have no claims on ergodicity breakings. But important point is that up to this disorder 6, we still see dynamics. And if this dynamics comes from that certain lyons have finite relaxation times, maybe that's up to disorder 6. They cannot all be fully conserved. That's it. Thank you very much.
Okay, thank you, Marcin. So I think now it's time for questions. Yeah, there was so one participant raised hands. Sumilian, you can go ahead.
Yeah, thanks. So I actually am a bit confused. So how do you know that? I mean, there is not a small delta function with a small residue, right? I mean, so you are somehow saying, I mean, because you are ultimately studying it over a short time, right? So how do you rule out that there is no residue still left? Meaning there is still, each leon has some small delta function with a small residue.
No. That's so that I mean, I think that this is what I sorry. That's what I want to say here. We don't claim that there is anything that here there is no delta function. We cannot say it. No. We just want to show that in this short frequency range, this relaxation time explains the dynamics. Of course, there can be something here, but still we have some finite relaxation times which follow this phenomenology here. We don't want to exclude any delta functions. Okay.
No, there is some delta function, but I think what I understood, you are saying all the leons don't have delta function, right? Some leons are decaying and there are less than 2 to the power L leons.
Okay.
So what I'm saying, maybe you can have 2 to the power L leons, but each of them have a small residue with some finite time decay, right?
So you would say that all lyons have delta function and this decay rate, yes?
Yeah. Yes.
This is really hard. This is really hard to distinguish. I think. I mean, this is really hard to distinguish for one reason. That's. I mean, of course. Why we cannot have stronger arguments? Why we cannot identify? Why we cannot call it phenomenology? Why we cannot identify these particular lyons which have relaxation time smaller than the TH? So okay, the first is we were thinking about it, but we should do calculations without averaging over samples. But the second important thing is we should do finite size scaling, because without finite size scaling, anything would have delta function. You know, we cannot do averaging over disorder, because that averaging for every disorder, for every single sample, there are different lyons, and then we cannot do averaging. But how to do finite size scaling without averaging over disorder? Yes? This is the key problem which we cannot solve. Yeah.
See. Okay.
We cannot exclude that this is really what that's what you are saying. Okay.
Thanks.
Yeah, I think Kuba is the next.
Yeah, thank you, Marcin, for the talk, and I apologize for interrupting so much. But
no, you are most welcome.
Because I was interested. But if you could show this plot of the other page of conclusions. Yes, this one on the right.
Yeah.
Yes. This main plot for different disorders and on the right, and as I remember, for Anderson case, instead of this tendency to go down with frequency to low frequencies, right, for this transformed imbalance, then you have flat lines, right?
Yes.
So what worries me a little, or maybe you have a simple explanation for my stupidity, is that if you increase the disorder, it seems that this curves bend more downwards. So if the flat is localized, so it means that with bigger disorder, you get, let's say, broader, bigger times, shorter times for Lyon's decay.
Okay, so look, this may be, I would need this plot. This will be the best, yes?
It's okay.
So you see, maybe I should stress it more clearly. We take the regular part then. The regular part means that we cut this diagonal part from operator, and we really, you can think that we cut this rectangle here only, yes? And then we do fitting in this rectangle, okay? Because the diagonal part is subtracted. And that's, these curves, they are flatter and flatter, but once you cut this smaller rectangle, it's not the case anymore. That's the trick, so that we don't fit this curve with delta function, yes? We take the regular part and we try to understand only this regular part, yeah. Okay.
Thank you.
So this is you see this curve going down. We take only the spectral weight from this frequency regime. So we magnify this rectangle, and then this rectangle is here in the conclusions. Yeah, here. Okay.
Okay, thank you.
Okay. Are there any other questions?
Maybe just a curiosity. I mean, you emphasize that, I mean, you cannot claim that there is ergodicity breaking or not in the thermodynamic limit, but just for curiosity, do you have any clue on how one could try to get any hints about the fate of ergodicity breaking or not in the thermodynamic limit? I mean, do you think there are ways to study this limit or not?
In the numerics, I mean, I mean, whatever I say, I will make many enemies, but
I see.
But okay, let me be honest. Yes, now, you know, the crucial point in the ergodicity are the orders of limits.
Yeah,
and we know, for instance, in the XXZ model, when delta is this anisotropy parameter is larger than 1, then these limits don't commute. You have different answer if you try to get these limits for simpler system. If you do this limit in the opposite way, yes. So that's why I think that any numerics here can be really criticized. Okay, it can be said, okay, guys, you do these limits in wrong order, and there is nothing you can show. That's why we wanted to extract some information. Maybe that was our aim, to go to the regime for which people cannot say that we do something wrong. Okay.
Mm-hmm.
Yeah, Zala raised hand as well.
Hi, Marcin. So is this mu then related to the dynamical exponent, or you are now presenting a different story?
No, this must be related. I didn't this, but this is, yes, yeah. But
so then somehow the subdiffusion is related to the decay of those decaying lyons.
Yes.
That's how the
that would be the scenario. That would be our scenario, that this is really that the subdiffusion would be related to the moment where we have lyons. I mean, there's decay times for lyons exactly. They have this broad power law distribution with mu smaller than 2. And maybe yeah, this mu smaller than 2 is not so strange, because you see, this is if tau max would go to infinity, if we really have subdiffusive system, I mean, if this is not transient but real subdiffusion, that for tau max going to infinity, for mu smaller than 2, this distribution does not have first moment. There is no average relaxation time, and that would correspond to subdiffusion. This would be the correspond to subdiffusion, where tau max is infinity, then this distribution has no first moment, yeah. But you are right. This would be really correspond to what we see. Okay, what we see. I think I was not too good with planning my time. If we do some finite size scaling of mu for different system sizes and different disorder, we almost always as far as we can, we think that we go to mu, which is small, which approaches 1. It's close to 1, approaches 1. Yes. Yeah.
So, sorry, this is what is diffusion? What would be diffusion?
The diffusion would be for mu larger than 2. Okay. Everything between 1 and 2, it would be subdiffusion. Yes.
Mm-hmm.
Yeah.
And this corresponds to having diffusion means no ions which are decaying at all.
Yeah, that would mean that all ions have the diffusion means that all ions, no ions, all have finite relaxation time. For finite system, this relaxation time is bigger than the Heisenberg time. So when we do any numerics for finite system, we see either transient subdiffusion or then this dynamics and then localization. This is one of the scenarios which are here that we can essentially, that tau max always stays below TH, the Heisenberg time. This is, I think this is the main question in our phenomenological approach. Yes. That there is,
Thanks.
Okay, thank you. So Elmer also raised hand.
Yes, maybe this is a stupid question, but why do you call it a Lion if it's delocalized? Are they not by definition localized?
we should know it. We should, these are okay. These are we try to find we use them delocalized. Yes. This is maybe even not the best name. That would be like perturbed Lion. Yes, that's they are not. We assume that they don't commute strictly with Hamiltonian. Yeah, you are right.
Okay.
Okay.
Maybe another. I mean, another simple question. Is there, I mean, to me, it looks like a magic that when you do this integral over omega, all the dependency on the ensemble realization disappear. Is it easy to see why that is the case?
Now you see, now try to, you see, these are numerical data, yes, for one realization of disorder. And now try to differentiate this data, which when they are close, you would see peaks. You will see peaks and some peaks and oscillations, which we cannot filter out easily, yes? That's it. These are peaks and oscillations, which come either from some finite size or some from, I don't know, maybe even from inaccurate numerics. And then, but they occur in the short time scale, yes?
In the short time scale, okay.
And then you do Fourier transform and you take only narrow window. Then you just,
I see.
You get rid of these high frequencies, yes?
I see. Okay. So you say that fluctuations are for high frequencies and you are integrating out that. So okay.
Yeah, we want to avoid this part of physics, yes, because this is different. We don't want to.
I see. Okay. No, now I understand the rationale behind. Okay.
Okay. Are there any other questions?
Yes, it
Jens, I think you raised hand.
Just this size dependence of, I guess it was mu.
Okay.
Interesting. So, first of all, there seems to be a minimum in it as a function of frequency. Do you understand that? And then also, you said that mu goes to 1 always. Is that true?
Okay.
Is there no weak disorder where you would get diffusion?
Okay. This is great questions. Do I have still time
Yeah.
So first this deep, and this deep I had no time to explain it. So do you see my screen now? Yeah,
you can make full screen as well.
I can make full screen. Wait. Okay, so you see, this line, continuous line, it comes from average spectral function. Okay, this is what everybody is doing, and that was also the minimum which you have observed on this plot which you are asking for. But we can do this we can do this fitting for each sample. And then we have this distribution of mu, which you see on the right panel. And once you get, once you do averaging from the distribution, this is different, yes, because for each sample we have distribution, and either we have average mu from distribution or single mu from average spectral functions. And this averaging over various realizations of disorder, we see that they produce this artifact, this minimum, because these averages, they don't have this artifact. These are the small points. So this is artifact. This is artifact from averaging spectral functions. And what was the second part of the, if we see diffusion at all? Yes, that's I can show you one plot here. This is very quick presentation. Yeah, it's here. You see. This is weak disorder. This is weak disorder, and then this is again this integrated spectral function. There is normal diffusion here at low frequency, or at very weak disorder is everywhere. And then you see that this anomaly, which is this anomalous power low frequency dependence, it gradually builds. We don't see, we see clearly diffusion here, but when you increase disorder, you need to wait a little bit because there is some transient subdiffusion here. Yeah. Yes, clearly the systems are diffusive. Yes.
Okay, thank you. Are there any other quick questions? No. Okay, let's thank. Then we thank Marcin Mierzejewski again. So the next speaker is Jens Bardason. We continue in 8 minutes. So there is now an 8-minute break. So I think we can, at this point, we can now stop recording or make a pause, and we continue in 8 minutes. Of course, the channel is going to be open, so everybody is welcome to chat. I will probably take a break for 3 minutes, and then we are back.